All right, welcome everybody to today's stream for PHYS 251RI, Computational Research Methods. We have pretty much gone over every sort of individual topic that we need to for the semester. And so what we'll do today is just a little bit of a recap, address any last questions that anybody has. I have not gotten too many questions over email. I did get one email that had a question with a final project attached to it saying, did I do this right? And the answer was yes, you did that right. So I've gotten that student's permission to take a look at their project number 3 as an example and inspiration for you. But otherwise, what I'd like to do today is just a little recap of the method for generating difference equations, and then take a look at a sample project 3, and we'll probably get done a little early today, I'm thinking, unless a lot of questions come flooding in to the chat or email. So I've got my whiteboard open here. We're going to take just a quick little review of how finite differences work. So finite differences or difference equations is a way of studying partial differential equations. So again, the idea is that you've got, let's say, Poisson's equation, where you've got d squared of f dx squared plus d squared f dy squared. So you got derivatives with respect to x, derivatives with respect to y. X and y are both independent variables, right? X and y don't depend on each other. That just means you're free to pick any point inside the region that you're interested in, right? You're not constrained to go along a line or to go along a parabola or a semicircle or something. You're eventually visiting every point along in the space. Equals, maybe this is equal to some kind of, charge density or source function or something over here. We'll call that rho. And the recipe is that all of your x values get replaced with a set of points along a grid. So we're going to divide the x-axis up into pieces here. Our textbook calls the distance between each of those a. So this might be 0a, 2a, 3a, 4a, 5a, etc., all the way up to na. And you do the same thing with y. You're going to divide the y-axis, into splices. And 9 times out of 10, it's usually good enough to space those out the same amount for this to be the same spacing as this. There might be a problem at some time in the future where you have to make those different, like maybe this is in units of meters and this one's in units of millimeters for some reason. Like maybe you're looking at the thickness of soil samples across a yard or something like that, and this is your position along the yard and this is the depth within the soil. Maybe you need those to be different sizes, but it's usually easiest to just use the same size a. The caveat is these are independent, right? So y has to have a different index. So I can have an xi and a yj. I just can't make those the same. The only time you would make those the same is if you're moving along, a particular line, because if those were the same, you'd be moving along a line, but you're not necessarily doing that. You're visiting any kind of randomly selected point along here. And so any point on here you can think of, instead of being x comma y, you can think of it as I comma j, because it's so many over in the x and it's so many steps up in the y direction. Now what that also means is any function, so f or rho of x and y, right? F has a different value at each one of these sort of randomly visited points. That needs to get mapped onto a 2-index thing, because this thing has an address at point ij. Right? X and y only get one index because they're moving along one dimension, right? You're only thinking about moving along the x-axis or moving along the y-axis. When you think about the function f, you're thinking about moving anywhere inside the square. And this just extends. If you wanted to do this in 3D, you'd have z changing to zk, and f would be fijk, right? So however many dimensions you have, that's how many indices your function has. And you do the same thing for rho here. The mathematical part comes in with these derivatives. So for a second derivative, so your second derivative of f with respect to x, I can write a better f than that, there we go, is going to change into f at the left or excuse me, f at the right, f of I plus 1 comma j, plus f to the left, fi minus 1 comma j. It doesn't really matter what order you write them in, but you do have to actually write the correct sign there, Brian. There we go. F minus 1 comma j minus 2 fij, the point that you're at. So think of this as the point that you're looking at. You're looking at a point to the right and a point to the left, and you're going to divide by your step size squared. And then when you want to do the second derivative with respect to y, you just do the exact same thing, except instead of going to the right and to the left, you go to a point above and a point below. So you have fij plus 1 and fij minus 1. This piece stays the same, which is handy when it comes to solving this partial differential equation. So this recipe, these 3 steps, changing your x and y's, changing your functions, and changing your derivatives, turns this differential equation into a difference equation, which you then solve for this thing here. You solve for the current value, and your goal is to take the current value and sort of iterate on it. So you're taking the points around it as sort of an approximation, and then you're going to make this better by looping around and getting a better value for each of the fij's each time you go forward. The only way this gets more complicated, should I say more complicated? I should say more nuanced. The only way this gets more nuanced is when you invite time to the party. So for your project 3, you're looking at the temperature in a rod. So you're going from 0 to L. And so this is along the x-axis. So we're going to splice this up just like we did before. Each of these has a spacing a. And you want to move it forward an amount of time h. So we're going to say t equals t plus h. So h is now your time step. Don't know why our textbook picked h for a time step, but it did, so we'll stick with that. And so you have the same splicings over here, but you're going to watch the function change in time. So originally your function had one shape, right? Maybe it looked like this. Maybe afterwards your function starts to look like this. It's going to time evolve, right? And the reason this gets different is because, let me go back just a second, I can't treat time the same way I did space, right? Because I can't go forward and backward in time, right? Once I'm at my initial time, I can't really go backwards a step. I don't really get information about what the thing was like at negative time. So what I have to do with this is treat my time difference a little bit differently. So if I'm taking df dt, that's going to get replaced by something else, right? So f now is a function of x and t. So again, we're taking x, we're splitting that up into pieces. We'll give that a label txi. We're taking t, and we're going to split that up into pieces tj. So you can think of I as going along this direction. So it's like your I is going this way, and your j is going this way. So think of I, so if you think of this as a movie, right? Videos are stored as a series of pictures. Each one of these is a different frame in the video. And so I is where you are located in the frame. So if you were to take a still shot, I is where is the point you're looking at inside the frame. J is which frame are you looking at. And if you needed to animate something in 2D or even 3D, you just keep adding indices, right? So you might have IJK for XYZ and then L for time or something like that, right? This method extends to multiple dimensions really well, really easily. But like I said, we can't really go backwards to a time before 0. So what we do is we say this is going to be f of I for x and j plus 1, we'll go forward in time, minus fij. So we're going from the current time to the next time, and then we're going to divide by h. Right? So if you do this symmetrically, if you go j plus 1 to j minus 1, you have to put a 2h, like we did for Poisson's equation. But here, we're just moving forward one step. We're just moving forward 1h, so we just put h on the bottom for our delta t. And again, you turn this into an algebra problem, so you take your differential equation, turn it into a difference equation, and you're trying to solve, not for that one, excuse me, you're trying to solve for this one, the next one. So this is how you take the current snapshot and turn it into the next snapshot. And that's pretty much it. The only thing that changes is what differential equation you are using. And so really it's just the expression for the next piece that changes each time, although they start to look similar after a while. So what I would like to do today is put out the call for any questions on difference equations that you'd like us to discuss. Let me know in the chat. And while I wait for those questions to come in, I want to take a look at a sample project 3. So I've had one student turn in assignment 3. I've had another student turn in project 3. So I know that these are doable at home. So if you are having trouble with these, if you're getting confused about these, let me know in the chat. Let me know over email. Let me know in office hours, later day or on Monday or anytime, and we'll take a look at it. So project 3 is all about the heat equation. So the heat equation is set up this way, where your rate of change of temperature is proportional to the concavity of the temperature distribution across the rod. So again, X is going across the rod. T is what your time is. So the T is what snapshot you're at. And so the goal we're trying to get out here is a graph like this, where we have temperature versus X for several different values of time. So each one of these curves is a snapshot of what the temperature distribution looks like in the rod versus position. So this is if you were to freeze, no pun intended, talking about the heat equation, if you were to freeze the rod at a standstill, if you were to just freeze that moment in time, this is what the temperature distribution would look like in the rod, right? You would have a high temperature fixed over here, you have a low temperature fixed over here. Initially, it's pretty roughly distributed, right? It's all kind of at this mid temperature. We haven't had a lot of thermal energy make its way from the endpoints to the middle. But as time moves forward, everything evens out and you're going to approach this equilibrium state, right? This purple is kind of what you would expect intuitively, right? You would expect it to go smoothly from the high temperature to low temperature. You wouldn't really expect these dramatic changes. And so what you're seeing as you go from blue to yellow to green to red, you're going forward in time. And you're seeing how the temperature of the rod kind of distributes throughout the rod, right? You're seeing how it kind of comes to a nice smooth equilibrium state. And the way we do that, this is the piece that has the finite difference equation, this line 35. Everything else is really just set up, right? So this is where we have the next step in time, we're calling that temperature prime, equals the current step, the current temperature at each point, plus all of this other stuff. So we've got C, this is just all of the constants thrown together. And then we have this piece that comes to us from the second derivative. So remember, your second derivative looks like, instead of thinking of it as an actual derivative, we're going back to a slope approximation. You've got the point to the right, the point to the left, minus 2 times the point in the middle. And what do you have over here? You've got a point to the right, a point to the left, minus 2 times the point in the middle. This is exactly what we had in the difference equation. Really, difference equations is just another way of rewriting your derivatives. It's kind of taking a step back in derivatives and saying, let's approximate the derivative as a slope, because the computer can handle slopes. It can't handle derivatives as a function, but it can handle slopes really, really well. And so we're just looping over this and saying, move time forward and repeat this thing. And then create the plots when we ask for them. So the way we get those plots is just by setting up a list of time values in t-lists. So this is saying, here are all the values of time that I want snapshots at. And so what you have to do for project 3 is add this piece into the loop. You're going to make the temperature at the left end of the rod change sinusoidally. And so here's what the student has done. The student who submitted this has taken this loop, right? This is the piece we were just looking at, this difference equation. And they've added one line to the loop. This line 36, this is the only thing they've had to add. Well, they also added some extra time values, but this is the only new line they had to add. They're taking they're taking temperature at the 0th point. So this is temperature at x equals x0. This is the temperature at the left edge. Is going to have a baseline value of t high plus this sine function. And so they've just taken this sine function from the instructions. They've written it in a way that Python can understand down here. And what do we get? You notice how the left end is no longer is no longer fixed, right? So just ignore the middle part for right now. Just look at this left end. So we start at the blue. That's starting out what we looked at before. We go to orange, then green, then red. You can see it's rising up, gets to a maximum, and then comes down. Sounds kind of like a sine function, doesn't it? Because that's what this is doing. It's making the temperature at the end oscillate up and down with a period of 5. So we should expect this thing to repeat itself every 5 time units. And sure enough, well, it actually color-coded 0 and 10 the same, unfortunately. But sure enough, if I look at the blue here, the light blue, if I can find it. Yeah, it's in the middle here somewhere. It goes up to the same point that we had initially. And so what's happening is you can kind of think of this as like a jump rope, right? This is like somebody tossing a jump rope and they're just using their wrist. They're keeping the jump rope end fixed. This is somebody who's swinging the jump rope at their shoulder. And so the end of the jump rope itself is moving up and down. This person's got a little bit more kinesthetic control over here. But yeah, that's kind of what it's doing. And so what's happening is that the temperature is trying to equilibrate along the way. We're trying to get to an equilibrium state along the way. So you still have this sort of approach toward a line. So if I look at, even if I look at this pink one, this t equals 2 seconds, it's gotten to a pretty good equilibrium state. The problem is that the left end is rotating. And so while I'm trying to get this thing at equilibrium, the left end is rotating. So I'm continuing to have to adjust the thing in the middle. And so you could play around with this if you wanted. You could, for example, change the amplitude of this. Let's suppose we triple the amplitude here. You notice how much wilder it gets over here. I haven't changed the period, so the time dependence is still the same, but I'm getting a much bigger kind of displacement here, much bigger amplitude. And look, we even caught a maximum in this gray curve and in this yellow curve, which is pretty cool. We weren't getting a maximum in the middle before, so that's pretty cool. You can also change the period if you want. You can also, if you want to, change the end point. So you could say Tn plus 1. I think there's an, no, excuse me, it's just n. That's right. You could do this as T low plus the same oscillation pattern. Let's see what happens with that. And here, I had to move the legend. Here, the right point is no longer fixed and the left point is no longer fixed. So you're getting all kinds of time evolution going on there. Let's see what happens if we change the period on this. Let's change this to a 7. 7 and 5 are not going to line up for a good while. Yeah, and so this is a really fun thing that you can play around with. There's all sorts of neat things that you can change. You can try different functions here. It doesn't have to be a sine. You could maybe do like an exponential increase up to an asymptote. You could do a power law, a 1 over times squared kind of thing where it's approaching 0 but not reaching it. Yeah, there's a lot of stuff you can play around with this. And again, the only thing you have to add for completing the project is these 2 lines right here. Show me what the graph looks like, and then discuss the results. So the student says, we are essentially putting a heat source on the left end of the rod and varying the temperature up and down. I chose more time values near 0. So the student is explaining why they chose to put more time values near 0. So when you want to examine this, you have to add in values to the t-list. So you see how this t-list is much longer than our original t-list. Our original t-list had 1, 2, 3, 4, 5 values. A student submitted a t-list to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. So they've nearly doubled the number of time values to get a better snapshot. And if this gets crowded, feel free to remove the time values that aren't telling you anything new, right? So if there's 2 curves that look pretty much the same, you can feel free to get rid of the 2 that are duplicated. All right, so that's pretty much what I wanted to go over. So let me know what questions you have in the chat. I'll give us a few minutes to look over those, but otherwise, formally, that will end our time together for this morning. I want to thank you all for your time and attention and for these awesome temperature graphs that I'm getting. This is going to be a fun project to review. Otherwise, thank you for your time. I'll have office hours later today at noon. I'll get you that link out in probably about an hour or so. All right, so in terms of semester scheduling, we've got kind of one more what would be a regular class next week. So we got one more live stream next week, and what I'll probably do on the 17th is just host. Well, actually, on the 17th, I'll be entertaining presentations for my other classes. So the 17th may be in flux, but I'll probably do the last week of the semester here is probably just host some office hour sessions rather than try to cram in more material. But what I might do next week, if I get more questions or requests for stuff that people want to look at, I can do another recap like today. Otherwise, I might do some bonus material. There was some interest earlier this semester in Monte Carlo integration, so I might do a live stream on that next week. That'll be a bonus. There won't be any problems or projects or anything associated with that, but I can do that as like a bonus piece of information for your enrichment. All right, I haven't seen any questions coming in, so I want to thank everybody for their time. If you are watching this after the fact, feel free to send in questions via email. Like I said, I think next week we'll take a look at some Monte Carlo integration, unless we have a flood of questions coming in. So thank you so much for watching. Have a safe and healthy weekend. And for students in my class, I will get you a link to office hours out a little bit later today. Have a great day. Bye-bye.